matrix by using elementary row or column operations. If A is a square matrix such that A inverse exists, then to find A inverse using elementary row or column operations, we write A is equal to I into A or A into I, and apply a sequence of elementary row or column operations till we get I is equal to B into A or A into B. In each case, matrix B will be the inverse of matrix A. In addition to the method discussed now, there is another method that is quite frequently used to find the inverse of a square matrix. Before learning this method, let's learn what the adjoint of a matrix is and some important theorems based on it. Consider a 3x3 square matrix A. Let Aij denote the cofactor of the element Aij of matrix A. On replacing the elements of the given matrix A by their corresponding cofactors, we get the matrix shown here. The transpose of this new matrix is known as the adjoint of the given matrix A. Hence, the transpose of the matrix obtained by replacing the elements of a square matrix A by the corresponding cofactors is called the adjoint of matrix A. It is denoted as shown. Now, let us see how we find the adjoint of a 2x2 square matrix, shown here. First, we find the cofactors of the elements of matrix A, which are as shown. Now, as per the definition, the transpose of the matrix obtained by replacing the elements of a square matrix by the corresponding cofactors is the adjoint of that matrix. So, the adjoint matrix has D and minus B in the first row and minus C and A in the second row. The adjoint of a 2x2 square matrix can be obtained by interchanging A and D and by changing the signs of B and C. Let us now prove an important theorem on the adjoint of a matrix. The theorem states that if A is any given square matrix of order n, then A into adjoint of A is equal to adjoint of A into A, which is equal to determinant of A into I, where I is the identity matrix of order n. Let A be a 3x3 square matrix, as shown here. By definition, adjoint of A is the transpose of matrix A obtained by replacing the elements of the square matrix A by the corresponding cofactors. Now, let us find the product of matrix A and its adjoint. The resultant matrix is as shown. This is equal to a diagonal matrix with each diagonal element equal to the determinant of A. This is because the sum of the product of the elements of a row or a column with the corresponding cofactors of another row or column of a square matrix is 0. Now, taking determinant of A common, we get determinant of A into I, where I is a 3x3 identity matrix. Hence, A into adjoint of A is equal to the determinant of A into the identity matrix. Similarly, we can prove that the adjoint of A into A is equal to the determinant of A into the identity matrix. Hence, the result is true for any given square matrix of order n. While calculating determinant of a matrix A, you often come across situations when it comes equal to 0. A matrix whose determinant is equal to 0 is said to be a singular matrix. Mathematically, a square matrix is said to be singular if its determinant is 0. So, here we can say that A is a singular matrix. On the contrary, a square matrix is said to be non-singular if its determinant is not equal to 0. For example here, the determinant of A is -2, which is not equal to 0. Hence, A is non-singular. Let's now learn a theorem which says that if A and B are non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. To prove this result, let us consider two non-singular matrices A and B of order 2 by 2 as shown. Observe that A into B is a square matrix of order 2 by 2, and its determinant is not equal to 0. Also, B into A is a square matrix of order 2 by 2, and its determinant is also not equal to 0. This shows that A into B and B into A are non-singular matrices of the same order as that of A and B. Next, we claim that the determinant of the product of matrices is equal to the product of their respective determinants. That is, determinant of A into B is equal to determinant of A into determinant of B. Consider the same matrices A and B. The determinant of A is equal to 16, and the determinant of B is equal to -6. So, determinant of A into determinant of B is equal to -96. And the determinant of A into B, as we calculated earlier, is equal to -96. This shows that determinant of A into determinant of B is equal to determinant of A into B. This leads us to a theorem which states that the determinant of the product of matrices is equal to the product of their respective determinants. That is, determinant of A into B is equal to determinant of A into determinant of B, where A and B are square matrices of the same order. Let's now move on to the next theorem, which states that if A is a square matrix of order n, then the determinant of adjoint of A is equal to determinant A raised to the power of n minus 1. Let's begin with the proof. In the previous theorem, we proved that A into adjoint of A is equal to determinant of A into the identity matrix. This implies that the determinant of A into adjoint of A is equal to determinant of A into the identity matrix. Now, recall the result that if M and N are two square matrices such that M is equal to K into N, where K is a real number, then the determinant of M is equal to K raised to the power of N into the determinant of N, where n is the order of the matrices M and N. Using this result, we have determinant of A into adjoint of A is equal to determinant of A raised to the power n into the identity matrix. Also, the determinant of the product of matrices is equal to the product of their respective determinants. So we further have determinant of A into determinant of adjoint of A is equal to determinant of A raised to the power n into determinant of the identity matrix. Now, the determinant of the identity matrix is equal to 1. This implies that determinant of A into determinant of adjoint of A is equal to determinant of A raised to the power n. On dividing both the sides by determinant of A, we get determinant of adjoint of A is equal to determinant of A raised to the power of n minus 1. Hence the result. Consider two matrices A and B shown here. On evaluating the product of matrices A and B, we get an identity matrix. That means matrix B is the inverse of matrix A, and vice versa. Such a matrix A is said to be an invertible matrix. Mathematically, a square matrix A is said to be an invertible matrix if there exists a square matrix B, such that A into B is equal to B into A is equal to the identity matrix. Now, let us derive one property of an invertible matrix. If A is an invertible matrix, then A into B is equal to an identity matrix. This implies determinant of A into determinant of B is equal to determinant of an identity matrix, which is equal to 1. This implies determinant of A is not equal to 0, or A is a non-singular matrix. This leads us to a result that if a square matrix A is invertible, then it is a non-singular matrix. The converse of this result also holds true. It says, if A is a non-singular matrix, then A is invertible, and A inverse is equal to adjoint of A divided by determinant of A. By Theorem 1, we know that A into adjoint of A is equal to adjoint of A into A, which is equal to determinant of A into the identity matrix. On dividing both the sides by determinant of A, we get the expression as shown. Now, comparing this expression with the expression A into B is equal to B into A is equal to I, we see that B is equal to adjoint of A divided by determinant of A. And as per the definition, B is the inverse of matrix A. So we have A inverse is equal to adjoint of A divided by determinant of A. Hence, A inverse can be calculated with the help of this formula, provided the determinant of A is not equal to 0.